Welcome to A-Level and AP Physics. In today's lesson, we will discuss important and tricky past paper questions from March 2021 paper 1-2. In this lesson, we will not only find the best possible option, we will also discuss why the other options are incorrect. This will help you to have a clear understanding of these concepts. For question number 17, it is given to us an egg of mass 25 grams falls vertically downwards from the surface of a table which is 900 millimeters above the ground. Air resistance in this case is negligible, and question is asking us we need to find out what is the kinetic energy of the egg when it hits the ground. This is pretty straightforward question, but the best way to answer this type of questions or any question in physics is to sketch. First of all, let's try to sketch so you can see a clear picture of this problem. For this question, it is given to us that there is a table and the egg is at the edge of the table. We can simply say this is the egg. Height of the table from the ground, this height is given. This is equal to 900 millimeters. Mass of the egg is given. The mass of the egg is 25 grams, or we can divide this one by 1000 and we can say this is equal to 0.025 kg. So this is kgs. This is 900 millimeters. We can convert into meters. We can also divide by 1000. So this is 0.9 meter. Now let's try to understand at this point. We have to understand what kind of energy it has at this point. It has GPE, gravitational potential energy, at this point, and let's say our reference, we have to set a reference line. Let's say at this point means at the ground the gravitational potential energy, this is equal to 0. So this is GPE at the ground, this is equal to 0. We can say this is GPE initial, we can write down, and we can say this is the final one. We also need to understand the kinetic energy here, the kinetic energy. So at this point the kinetic energy is equal to 0 because the egg is not moving. Question is simply asking us what is kinetic energy at this point when this egg will hit the ground. So this kinetic energy we need to find out. Now we can also say that this is initial kinetic energy and this is the final kinetic energy. Simply we need to use law of conservation of energy to find the kinetic energy of the egg. So by law of conservation of energy, we can simply write down by law of conservation of energy, initial kinetic energy and initial GPE means the initial energy has to be equal to the final energy, total energy. We are talking about total energy. In this case, the initial energy, that is equal to initial kinetic energy, means the sum of initial kinetic energy and sum of initial gravitational potential energy. This has to be equal to the final kinetic energy plus the final GPE potential energy. Initial kinetic energy in this case is equal to 0, so we can write down, but initial GPE, this is equal to mgh. Final kinetic energy, this is what we need to find out, so simply we can write down this is kef plus final potential energy, this is equal to 0 because we have taken this reference point and here potential energy is equal to 0. Simply in this case we need to understand kinetic energy final, this is simply equal to mgh. M in this case is 0.025 times 9.81. You have to use 9.81, not 10. Height is 0.9. Now simply we need to multiply. If we multiply this one, we will get this is equal to 0.22 joules. So this is the final answer. So that's the answer for this question. For question number 18, it is given to us an aircraft travels at a constant velocity of 90 meters per second in horizontal flight. Drag force acting on the aircraft is given, that is equal to 2400 newtons, and mass of the aircraft is also given, and this is equal to 2000 kgs. For this question, we need to find out what is the power produced by the thrust force. For this question, it is given to us aircraft is traveling at constant velocity. Constant velocity means that the forces acting on this aircraft are balanced, or simply we can say the net force on this aircraft, this is equal to 0. We can also say that in this case, because thrust is acting to the right, so thrust is acting to the right and drag is acting to the left. So these two forces, there are only two forces acting along horizontal. We can simply say that in this case thrust is equal to drag. These two forces are equal. And drag, the magnitude of drag is given, that is equal to 2400 newtons. It simply means that thrust is also equal to 2400 newtons, but thrust is acting to the right. So this is magnitude of thrust. Now we need to understand how we can find out the power produced by the thrust. Power is rate of doing work, means this is equal to dW by dt. Work, we understand, work is equal to force times the distance moved in direction of force. Simply we can say W is equal to Fs. Now we can replace W with Fs. Simply we can write down here. If the force is constant, means if force is constant, we can take force common, then we left with ds by dt, and this is the velocity. It simply means that power is equal to force times velocity if the force is constant. So very important point, when to use this formula when the force is constant. Now simply we can use this one and we can find out the power produced by thrust force. This is thrust times the velocity of the aircraft, so we can say this is the velocity. Thrust force in this case is equal to 2400 newtons. Velocity is equal to 90 meters per second. So simply we multiply these two quantities, our final answer will be 2.2 times 10 to 5 watts. Answer for this question is B. That's the answer. Question 19 is simply asking us to find the expression which is equal to the stress on a wire. If you look at option A, first of all, option A, this is simply delta x over x, and that is equal to strain. So the first one is not stress because this is equal to strain. Now if we go to second one is force over cross-sectional area of the material, and that is stress. So this expression is for stress. So our answer for this question is B. Let's look at C now. For part C, we need to understand it is given to us force over delta x, and force over delta x, this is equal to K, or simply we can say this is equal to spring constant. Another important quantity, this is spring constant. Let's try to find out what is Young's modulus over original length. First of all, let's try to understand what is Young's modulus. Young's modulus is simply equal to stress over strain. We can write down this is equal to stress over strain. Stress is equal to force over cross-sectional area, and the strain is equal to delta L by L. Now if we rearrange this one, then simply we can write down this is FL over A times delta L. But the expression here is Young's modulus over original length, so we can write down this is Young's modulus divided by L. So this is L naught in fact, so the original length. We can add this is L naught, so this is L naught, and this is equal to F over A times delta L. F is simply, it is the force, but A times delta L, this is the change in volume. So Young's modulus over original length, this is simply equal to force over change in volume. For question number 20, it is given to us a wire is stretched by applying increasing values of force F. For each value of force applied, extension X is recorded and a force extension graph is plotted from the data obtained. Question is asking us which statement about the area under the graph must be correct. First of all, let's try to understand force against extension graph. If you look at this graph, you can simply see we have this one curve, and this curve is the loaded curve. Means when we apply force on the wire, simply we can say this one is the loaded curve. And the second one, let me use a different color. This curve is unloaded, means when we remove force. So this one is unloaded. We can write down the second one. This is unloaded curve. And the area between these two curves, this area is equal to X. So this is area X. And area under unloaded curve, this area is equal to Y. Now the sum of these two areas means area X plus area Y. This is equal to the total work done in stretching this sample or this wire or this spring. So that is equal to total work. But X means the area between these two curves. This is equal to amount of thermal energy produced, or simply we can say the amount of energy converted into heat energy. And the area under this unloaded curve means area Y. This is representing elastic tension energy, and this is the amount of energy stored in the wire, and this is also amount of energy that will be recovered when we remove the force. So this is very important point you need to understand about this curve. There will be a lot of question about this, and you will see question on this curve every year in past paper question, especially in paper 1. You can also understand this one based on if you have graph stress against strain, then the area under unloaded curve, that is also equal to elastic tension energy, and area between these two curves, that is equal to the heat. And elastic tension energy plus heat, if you add these two, that will be equal to the total work done by you in stretching the wire. So that's all what you need to understand about force extension graph and stress strain graph. Now try to answer this question. We need to find out which statement about the area under the graph must be correct. If you look at the first one, it is telling us it can be calculated by 1 over fx. This is not true always. Why it is not true always? Because if the spring or wire does not obey Hooke's law, that will not be true. So let me explain to you with this force extension graph. This is only true if the wire obey Hooke's law, means like this. It obey Hooke's law, then area in this case, that will be equal to the area of triangle 1/2 fx. Only if it obey Hooke's law. But if it does not obey Hooke's law, we cannot calculate area using this formula. If you look at option B, it is given to us, it is the elastic potential energy stored in the stretch sample, EPE, elastic potential energy. It simply means that the total work done by you, it has been stored in the wire in form of elastic potential energy. And when we unload the wire, there is no thermal energy produced. Means the total work done by you has been stored in the wire in the form of elastic tension energy, and when you release the wire, means when you remove the force, all the energy is recovered, and that is only possible if the wire deform elastically. If the wire is deformed plastically, that is not possible. So B is also not best possible option. If we go to C, it is the work done in stretching the sample. It's simply telling us it is the total work done, and this is always true. So the best option is C, and this is true when the wire is deformed elastically or plastically. So this is the best possible option. If we go to option D, it is given to us it is same for any wire of same material. This is not true, because for the same force, if the force is the same, extension is different. If wire has different dimensions, so the area under the graph will be different if dimensions are different. So this is also not possible option.